Hi everyone. Today let's look at this interesting problem. It's the LeetCode problem 875, Koko eating bananas. This is a very good problem. I really like this problem. So let's just go through this problem now. Koko loves to eat bananas. There are n piles of bananas. The ith pile has piles I bananas. The guard have gone and will come back in h hours. So you are given n piles of bananas and each of them tells how many bananas are there. And the guard takes a break for 8 hours. So here the guard took a break for 8 hours. Koko can decide her bananas per hour eating speed of k. Each hour she chooses some piles of bananas and eats k bananas from that pile. If the pile has less than k bananas, she eats all of them instead and will not eat any more bananas during this hour. So now what this problem states is Koko can decide what is the maximum limit of bananas it can eat per hour. And so now the thing is, this k is something that we have to derive in this problem. And there is a condition for this k. So Koko likes to eat slowly but still wants to finish eating all the bananas before the guard returns. Return the minimum integer k such that she can eat all the bananas within h hours. Okay, let me reiterate the problem once more. I think that makes it much better. So we are given a piles of bananas. Okay, so for example, you can see here, right? Pile of I or pile of 0 tells that there are 3 bananas, 6 bananas, and so on. Now there is a guard. He has gone out for 8 hours. Now we have to find a minimum value of k, that is the bananas per hour for Koko, that would allow her to finish all the bananas before the guard comes back. This should be a minimum k. For example, if you see, right, if I take 11 straight away, then you could end up finishing, so it will eat 3 in the first hour. So that is one condition. So if there are lesser number of bananas than the value of k, then it will only eat that many bananas that hour. So it will be like in the first hour it will finish 3. It will need another 1 hour, and 1 hour. So 4 hours it would have finished everything. But what we want to find is the minimum value of k. Now let's see how to do this problem. Let's start with a brute force approach for this problem. Given this, since it's minimum, let's first set k is equal to 1 and see what happens. So if you see here, this will end up taking 3 plus 6 plus 7 plus 11, which is way greater than 8. Okay, I'm not even summing it. All right. Now if I take k is equal to 2, now in this case, for the first, we'll take this example. Okay, so in the first hour it will take 2 hours. In the second is for the second one, since it's 6, it will take 3 hours. For the third one it will take 4 hours, and for the last one it will take 6 hours. So that's also way greater than 8. Now if you take k is equal to 3, then this would take, of course, you can see, right, this will be 1 hour, this will be 2 hours, then this will be 3 hours, and finally this will be 4 hours. So that is also equal to 10, which is greater than 8 hours. But now if you see k is equal to 4, then this will be 1 plus 1 plus 2 plus this will be 3, right? So this will be 4 plus 3, 7. The minimum value for k is 4. Imagine the size of array is n. Size of array is n. Then for the brute force approach that we mentioned above, where we are linearly searching from k is equal to 1. So all right, so we are putting linear search here, okay, of k from 1 to max in array. It will be assuming this value range is k, then our brute force approach will be order of nk. I hope this is clear, because for each k we have to iterate through the array. All right, can we do better? Now you see a pattern here, right? So now what is the range of values k can take? K can take values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. These are the values k can take, because beyond that it doesn't make sense, right? So because in 1 hour Koko can eat at least the one given pile. Can we use binary search here? Okay, so now the idea is that we can start doing a binary search on our array. So then that means k we'll find the midterm, which is 1 plus 11 by 2. So that will get me to 6. So now if you see here, if I use mid is equal to let me put it here. So let's take mid here, right? So this is mid. Okay, I'll just put m here. Okay, so now if you take 6 and if I make k is equal to 6, then the minimum time that it will require will be, let me paste the array here, sorry. If you see here, it will take 1 plus 1 plus 2 plus 2. So that is 1 plus 1, that is 2 plus 4 plus 6. So 6 is less than 8. But is this the solution? So this is like, we now need to see if we find a value, an ideal value of k, which will allow Koko to finish in a time less than h, which is 8. Then we can still search to its left to see if there is a lesser value. Okay, so what we'll do is we'll store the result for the time as 6, and then we'll do a left search. So what will happen is we will reduce the load to m minus 1 and then keep searching left. So what will happen is we'll come here. Then it's like your normal binary search, and we'll just keep going towards the left. If you let me just finish this problem for you. So now what will happen is this will be 1 plus 5 by 2. So now k is equal to 1 plus 5 by 2. Okay, so this will become 3. Now if I take 3, we had already calculated 3, so I'm just going to put it here. So this will be greater than 8. So now what will happen is we will move the load to, this will become, it will come here, and this was here. So now what we'll do is we will take 4 plus 5 by 2 is equal to, this will be 4. So k will be 4. So if you look at k equal to 4 earlier, then this will be the value. So now what will happen is we found k which is less than the previous value. So what we'll do is we'll take res equal to 4, and then we'll again move k back to, sorry, the load to mid minus 1. So imagine this was, so m was here, okay, and this was L and this was high. Then what will happen is we will move high here. So that means our low is greater than high, so we can stop the search. So the result will be 4. I hope the explanation is clear. In this case, our time complexity will be order of n into log k, because we are doing binary search. So this will become n log k, and space complexity is order of 1. So we will have a faster algorithm here. Now let's look at the implementation. To start with, let's have 2 variables which will be helpful to do the binary search. Basically it has to be the max element in the array. Then now we'll try to determine the min k. Okay, so now we are going to do the typical binary search, find the mid element. This is just to avoid overflow. You could even do a low plus high by 2, but this I will avoid overflow, actually, integer overflow. Can Koko finish eating? Okay, here we will pass piles for this given k, that is mid. Can Koko finish the piles? So we will have a private function for this. Now let's try to calculate the total. What we'll do is we will just do a total plus equal to, so we'll do a rounding up for the division. So per hour you can have p by k. So how many hours you need is p by k. Then what we do is if total is greater than h, straight away we can tell that we cannot have it. Else we'll calculate the total and then just return true. Now if this is true, then see if we can have a lower k. So if so here this will become k is equal to, so this should not be k, this should be mid. K is equal to mid, and then what we'll do is we'll still continue searching to the left. So this will be high is equal to mid minus 1. Okay. Now the other case is we will now search to the right because we are crossing the time. So that means low is equal to mid plus 1. Then we'll just return k. Let's see. Looks good. Yeah, so this looks good. I hope this is clear. Have a good one. Thank you.